We are Group 71 and we explored on neural network surgery for deep reinforcement learning. Exploration on ANN architectures is today still a highly time-consuming task. After changing the input, output, or architecture, weights need to be retrained from scratch. This becomes a big burden in custom deep reinforcement learning environments, when while modeling agents' policies, such changes are very common. Transfer learning can help in this task. Recently, OpenAI published a paper describing a method to clone weights between ANN policies. Nevertheless, they decided not to share their implementation. We took it as an opportunity to provide an open source code that achieved the same goal. Given a trained policy and an untrained modification of it, we run an algorithm which transfers the weights from one to the other in such a way that the new model performs significantly better than starting from scratch. To do so, we first pair the layers of both models, according to a set of IDs given by the user, as well as identifying newly added layers. We establish new inputs and outputs thanks to the list of IDs set by the user. Subsequently, our algorithm runs these IDs to the network, copying the new weights from the paired layers, in such a way that the learned input-output relationships are kept. Newly added layers are initialized so that they modify as least as possible these relationships. As for now, we have implemented this algorithm to work both with dense and 2D convolutional layers, for both TensorFlow and Keras-RL. As a sanity check, we tested the weights transfer capabilities of our method on 3 well-known supervised learning benchmark datasets. The first experiment was on the Titanic Kaggle dataset. This one consisted in first training a model with a subset of input features. Then transplant the weights into an untrained model which accounted for all the input features. As you can see, the transplanted model starting loss, in green, is significantly lower than the one starting from scratch, in blue. Its convergence is also marginally faster. We also tested our algorithm performance when augmenting the number of outputs in a supervised regression task. In this case, we first trained a model which predicted the house price given some features. Later, we translated the learned weights into a model which also predicted the house area. As you can see, the model which received the previous weights, also in green, learned much faster than the one starting from scratch, in blue. To verify our convolutional weight transfer, we trained a CNN to classify means numbers from 0 to 3. Then transferred the weights in a network used to classify numbers from 4 to 9. Again, the transplanted weights model learned significantly faster, even though their weights came from a network which classified different numbers.
We test the approach in 3 reinforcement learning problems. The first is cart pole. The goal is to balance a pole by controlling a cart. At each step, we observe the cart position, velocity, the angle of the pole, and the velocity at the tip of the pole, and we decide whether to push the cart from the left or from the right. As first experiment, we train a model that can only see the velocity of the cart and the angle of the pole. Then, we transfer the learned weights into a new architecture that, this time, takes as input the full observation space. As we can see from the results, the model, green line, now performs better with a high margin. For comparison, the blue line in the plot shows what would have happened if we trained the new architecture from scratch. We now use the whole observation space from the beginning. The weight transfer technique again shows better performances if we increase the number of units in the hidden layers from 4 to 16. Again, if we transfer the weights into a new architecture that has one additional layer, we gain in performances with respect to training from scratch. We now test the technique on the acrobat problem. The goal here is to swing the links above the given height. We can only control the first joint. We can observe information about the joint angles and angular velocities. We train a model that can only perform 2 actions: apply a torque clockwise or do nothing. We then transfer the weights into a new model with 1 additional output, corresponding to the remaining torque counterclockwise action. Results show how the weight transfer approach, green line on the plot, outperforms training from scratch, blue line in the plot. As last experiment, we test the technique on a more complex task, the lunar lander problem. In this environment, we have to land in the flagged area. We can fire from any of the 3 propulsors or do nothing. At first, our network has only 2 outputs corresponding to firing from the left and right propulsors. We then move the weights into a new network that has 4 outputs, adding the do nothing and fire from the center actions. As the results show, the weight transfer techniques achieves better performances when compared to training the model from scratch. As conclusions, our results show that when modifying a network architecture, using the weight transfer technique is preferable to training the new model from scratch. As reinforcement learning trainings are often extremely long and their design required to modify the network structure frequently, we argue that weight transfer technique should become a standard workflow in reinforcement learning research.